Let's go through Lexical 3403. Find the lexical largest string from the box. And for this question, there is one and two. The only difference is that the word length, this is the 5 to the power 3 time length, and the other one is the 5 to 2 to the power 10 to the power 5. So the thing that the code of 2 should be able to apply to code 1. The question is asking, giving a word and a number of friends. That is, we want to, let's say, this word have length n. We want to separate this word into k substrings, and this k substrings should be able to have no overlap, and also be able to compose this kind of word. And let's return the largest lexical substring. So for this question, we'll say if we have we're trying to find the largest lexical one, right? So we know the other character should at least be have one character. The other have at least one character. So that means for this substring, it need to have n minus k. This is k plus minus 1. We use k minus 1, so should be the length of this, right? Um, because if we have a substring which is smaller, for example, this is I to j, right? We can also have this substring extend to I plus this kind of length, right? Should also always be greater. And so we'll see the result will always have this kind of length. And for this question, let's assume already we find there is something called the largest lexical substrings. For example, we have largest substrings is here, right? And there is some other substrings which is this. And we find this, then we get get the prefix of this length, right? Of the largest so that will be our result. And for example, this is m, right? Or the largest is smaller than m, right? We prefix we just get the largest one. So let's prove this. If we have some other substrings, right? So we'll say this is A and this is B, right? So I see the B is the largest lexical. So that means there is some character which is C1 and C2, right? At least the C2 will be greater than C1, right? So the thing is that if the C2 greater than C1 is out of this part, out of the M minus K plus 1 part, right? So that means this substring will be equal to this substring at least, right? So if we are finding the largest lexical, this one will at least be equal, right? And and um and then the other scenario is that this character, for example, is in the range. That means, um, that means, of course, this prefix is greater than the other candidates. So if we find the largest lexical substrings and we get its prefix, it will be our result, right? And if for this one, this is smaller, right? That means uh, smaller than this kind of range. That means for at least for this kind of range, right? There is there is no substrings um have the same, right? So there must have some characters uh in any of this kind of lengths. This will be greater, right? Otherwise, it can extend to the end. So, so, so in any way, we find the largest lexical substrings. We get its prefix. Prefix can either to be a minus k plus one, right? Or prefix if it is this one, it's extended to out of the range, right? So if the largest lexical is smaller than this, we just get written the largest lexical, right? So this question it convert to find the question 1163, the last substring in lexical order. So um for one for 1163, find the last lexical string. Um, we can do O(n) time complexity. So how can we do that? So what we do is that we are actually compare, for example, compare those kind of characters, for example, I to N, right? Because we know the last lexical greatest will always extend to N. Otherwise, uh, if not extend to N, we can let it to extend to be greater than the one not extend to N, right? So what we do is that we are comparing as I plus 1 to N, right? So, and until as J to N, right? So this is the process. So, so the thing is that what we do is that if we have, for example, S J to N is greater than S I to N, right? Then what we do is that we will move I to N to J's position. And we have J to move to some later position, right? So this J can move at least to J plus 1. So that we know on the left pointer, this string, when we compare, is that from I plus 1 to N, right? S plus 1 to N to Sj minus 1 to N. They are all smaller than Si to N, right? So if we find a greater, then we move our I to J's position and J to our later position. Um, so how can we compare those kind of characters, right? So the thing is that now let's assume we are comparing these two strings. One is the SI and SJ, right? SI SI to N and SJ to N, right? So the process we are comparing is that first we compare the character SI whether it to equals SJ, right? So if we compare SI plus 1 whether it equals SJ plus 1, right? So until, for example, we find S, this character plus K doesn't equal to SJ plus K, right? So if it doesn't equal, um, there are two scenarios. So if S J plus K is greater than Si plus K, right? So that means this J to N string substring is greater than I to the N substring, right? So in this case, we'll have I is going to move to J, right? But where should we move J, right? J should be at least to be J plus 1. But we can have J more aggressive. So I J, right? So for example, we are comparing. Let's see. Let's put J here. J is here, right? And so let's say I plus 1. This equal, right? This equal. And this equal, right? This is equal again. Let's use another color. And for example, this equals, and this equals, and this equals, right? Until I moved here, and J moved here, right? So I plus K is here. So if we have this character, it's greater. For example, this is C2, this C1, right? We'll have C2 greater than C1. So, so the things that for this part, right? J to this delta, so I plus K minus J, right? This part. This part, if we shift to this part, right? It already been calculated that they are because the Si plus 1 they are smaller than Si, right? So all of this they are smaller than all of the character here is smaller than Si, right? So that means for the J plus 1, these kind of substrings, right? They will be smaller than Sj, right? So So this will never be a candidate, right? So we can have our J's position to move here directly, right? So that is our J can be max J plus 1 and I plus J plus K minus J, right? So this is one of the optimizations. So if we have this C2 greater than C1, right? Um, if this C1 pass J, we can move to C1 the index plus 1 J to the index C1's index plus 1, right? So another thing is that if we have C1 greater than C2, right? Then, of course, our I we cannot move. We can have J, for example, at least to be J plus 1, right? But the thing is that actually we can also do aggressive. For example, we have C1 greater than C2. That means um, that means um, we know this J plus 1, right, is the same as I plus 1, right? Because I plus 1, Si plus 1 is smaller than Si, right? So J plus 2 is this character is same as I plus 2, right? So that means in the range from I plus 1 to I plus K, right? I plus K. Um, those kind of substrings is always smaller than Si, right? So that means from J plus 1 to J plus K, those kind of substrings is also smaller than Si, right? So we can have the J move to J plus K plus 1, right? So that is another optimization. So in this case, we can do have two pointers and can let our time complexity decrease to be On, right? So let's write code for this. So we'll say if this kind of non-friends equals 1, we just return word, right? So what we do is that int n equals word dot length, and we are going to have I index equals 0, j index equals to 0. So have yj smaller than n. So we're going to have k, right? K equals to 0. That is used to compare character by character. So we'll say while j plus k smaller than n and word char at I plus k equals word char at j plus k. In this case, we're going to increase the k, right? We increase. And we'll say if j plus k is smaller than n and word char at I plus k is smaller than word char at j plus k, right? So in this case, we are going to move our I to j, right? So we'll have I will be j, right? But since that we are going to have move our j to be max dot max, that is j plus 1, and the I already changed, right? So we use a temp. So that will be t plus k plus 1, right? And else we'll have we I should not change, but have j will be j plus k plus 1, right? And in the end, we trying to get its prefix, return prefix. So that since that it is possible, the prefix, this lexical length is smaller than this I minus minus k minus plus 1, right? So we're going to use word substring I to mass dot min n I plus n minus num friend plus 1, right? So this will be our code. Yg k equals mass min I let's set this one as 1 instead of as 0. It will be a problem when this is at 0, right? Because we are comparing the same character, right? So same substring. So doing like this, the time complexity will be O(n) and the space complexity will be O(1). Also, let's write the Python code. If num_friends equals 1, right? Just return word. Then we'll have nij equals length of word and 0 and 1, right? So what we do is while j is smaller than n, let's have a k, right? So while j plus k is smaller than n and word I plus k equals word j plus k, then we'll keep extending, right? K should plus equal to 1. And then we'll say if the SD is greater, right? So that is j plus k is smaller than n and word I plus k is smaller than word j plus k, right? If this character j plus k character is greater, well, let's have a temp, for example, t equals I, then I will move to j's position, right? J will move to max, at least j plus 1, right? But if I plus k plus 1 is already exceed j, right? We can have this one to move to t plus k plus 1 directly. Yes, we'll just have we keep the ith position, but have j equals j plus k plus 1, right? So in the end, we just return word from I to mean either that is n, right? That otherwise, or I plus n minus num prime plus 1. Right?